in section 5.8, analyzing graphs of polynomial functions. So here we are, we've wrapped up our chapter 5 here with this section. This is kind of getting us to the focus point, I think, of the chapter, and that is how do we take all this information we've been learning about polynomials, factoring, rational zeros theorem, grouping, finding zeros, finding factors, and what do we do with them now? So we've been talking about all of these components, and we're going to finally get to take a look at the graphing piece of the puzzle now. So this is where the application would come in. You are working in an office, and you've gone out and gathered data, and this data then comes back and is put into a spreadsheet or something, and you generate from that some sort of a graph, and then your goal is to create from the graph some sort of a function, an equation that you can use to extrapolate, interpolate data for future references. So here's the summary of where we've been so far. Polynomials and their zeros, which is again a value where my graph produces a y value of 0. Zero is the x values that make y equal 0. The zeros in turn, and again we've been using this notation for 0k. The zeros in turn help us to find factors, and we've been using this notation x minus k for our factor. Solutions, we have, again, the value of k, which is our 0, is a solution of the polynomial when f of x is equal to 0. So zeros and solutions are synonymous right there. And then x-intercepts, also referring to our value of k, where our y is equal to 0. These are again, the things that we're going to use for graphing, but they are, all those are related. So that's where we've been, and now we're going to go ahead and do some graphing. One other note on the zeros, remember that the x-intercepts, they're the real number values of zeros. When we were doing some of our rational zero theorem a couple sections ago, we discovered that some polynomials have real zeros and some of them have imaginary zeros. And so zeros and x-intercepts, the difference being the x-intercepts have to be real numbers. They're plotted on my number line. Okay, so when we're graphing these polynomials, it is super important that we understand that it's way easier to graph a polynomial when it is in factored form. Well, in these first couple examples, we're going to see them in factored form, but just a mental note, factored form for graphing. Especially when we're doing this stuff just by hand, we're not getting the help from our graphing calculator or something, which is another way we could come up with the graphs. But you still need to know where those graphs are coming from. So, all right, we have f of x equal negative quantity x plus 2 times quantity x minus 1 squared. All right, so if we're going to graph these polynomials, we've been talking about end behavior. We've been finding zeros, and we've talked about how in the zeros there are some cases where our graph is tangent to the x-axis, which meant it bounced off of the x-axis. And there are other cases where our graph physically crosses the x-axis. So we're going to go and revisit that now. In terms of the end behavior, we need to know two things. We need to know the degree of the function, and we need to know the leading coefficient. So these two things will help us identify what's going on at the end. Not so obvious to see what the degree of the function is, nor is it obvious to see what the leading coefficient is. However, you can quickly kind of come up with this by doing the following. In terms of the degree of the function, basically look at your powers that you have in your factored form. We have an x to the first power. we have an x to the second power. So really you've got an x to the first times an x to the second, which means you have a cubic function right here. So I know my degree is 3. More importantly, it's odd. Now I know that my graph's either going to start in the upper left and end in the lower right, or it's going to start in the lower left and end in the upper right. Now the lead coefficient maybe, again, not so obvious, but if I looked at foiling or distributing these binomials out here, and I get to a place where I can see that I have an x times an x squared, and then I've got this negative that's hanging out here, I'm going to end up with a negative x cubed. So I know that my lead coefficient is a negative value for this graph. If you wanted to, you could take those binomials there, go ahead and distribute them, and then write the function out in its expanded form, and then you'll very easily see what the degree and the lead coefficient is. But those are some quick ways you can come up with that without having to do the expansion part. All right, then what do we do? Well, then we want to look for our zeros. And we look for our zeros in the factored form by setting our function equal to 0. And then using our zero product property to come up with these values. So this negative that's out in front, that negative is just telling me that my graph is starting in a certain spot. Factor-wise, I really only have 2 factors going on here. I've got x plus 2 as a factor and x minus 1 as a factor. That negative is not a factor. So when I'm finding my zeros, I do x plus 2 equals 0, which means negative 2 is a 0. And then I have x minus 1 quantity squared equals 0, which means I square root both sides, get x minus 1 is equal to 0, and x equals 1. This 2, though, is useful information for me. So we have 2 zeros. Yesterday we were looking at a situation where my zeros, if I knew that the power on that binomial was an even number, as is the case here. So when we have our factored form and we're looking at the power of those binomials, if it was even, that meant that our graph was tangent to the x-axis, and we were bouncing off of that value. So we're going to physically bounce off of the value x equal 1 here. X plus 2 had a no power shown, so that means it's 1, and it's an odd. And an odd power we learned yesterday was when my graph crosses the x-axis. So I have one place where my graph is going to cross, negative 2. I have one place where my graph is going to bounce or be tangent to the x-axis at 1. So we go ahead and we put our points in here, our x-intercepts, negative 2 and 1. And then we go ahead and we graph them. Put them up this way. And we go ahead and we graph this thing. Now, it's an odd function with a lead coefficient of negative, so it should be starting above the x-axis, coming through negative 2, making a turning point somewhere between negative 2 and 1. And then going up to negative, or up to 1 and bouncing off of it. So it would look like this. And there's our graph. So it's super important that we understand both these concepts of zeros and in behavior, because then they together help us get a full picture of what's going on with our graph. Now, we are not going to focus on finding the actual local minimums, local maximums. We'll talk about what they are in just a second. We're not going to find all of the points along this curve. You can if you want. You're more than welcome to do that through synthetic substitution, or just put some t-tables together and pick some x's and find some y's. But we're not going to be after like the exact value of this local minimum. You can estimate it somewhere in between 0 and negative 2, or maybe halfway between 1 and negative 2. You can use that point, but we're not going to go after the exact value. I just know that in this case, that local minimum exists between my 2 x-intercepts. We're really just looking for the shape right now, and when you guys get into calculus, we'll worry about the local mins and maxes in terms of their exact values. All right, so there's that one. Let's go ahead and try another one here. So again, identifying what we need to see the full picture of the graph. We need our end behavior, and that means our degree on this one. Again, power of 2, power of 1, add them together, I get an odd degree. This is a cubic. My Lie coefficient, x squared, x to the first, and then I've got this 1/4 out here. That's helping me determine my Lie coefficient as a 1/4 x to the third power. So I know that I have a positive leading coefficient here. In terms of my zeros, again, take your factors. Now, 1/4 is not a factor. I'm not solving for an x. There's no x associated with that 1/4. It's x plus 1 squared is a factor, and x minus 4 is a factor. And we get -1 and 4. And again, because this is a power of 2, we're going to bounce off of x equal -1. All right, so we go in and we determine it's an odd coefficient with positive Lie coefficient, or odd degree with a Lie coefficient that's positive. It's going to start down in the lower left, so quadrant number 3. It's going to end in quadrant number 1. It's going to go through x equal. It's going to have an x-intercept of x equal -1. It's going to have an x-intercept of x equal 4, but it's going to bounce off of that -1. So here's what it would look like. All right. And again, we see that this graph has this low area, local minimum, and we're just going to look for the shape. Now, the further apart our x-intercepts are, the lower our graph will dip, or the higher our graph will go. So the closer our x-intercepts, then that change from the x-axis, that difference from the x-axis gets smaller. The further they are away, again, we get that distance from the x-axis grows. All right, so those were our first two. Now let's take a look at what we were talking about here a little while ago, and then that is our local minimum, local maximum, and then we're also going to talk about these things called turning points. So the turning points are the places where our graph changes direction. They correspond to these areas that we refer to as local maximums and local minimums. Now, if you looked at a cubic function, as in the example over here to the right, this example, you'd say, if I asked you what the maximum value was or the minimum value was, well, the fact that the graph keeps going for positive infinity in the y direction indicates that it doesn't have a maximum. And the fact that it's going negative infinity in the y direction indicates that it does not have a minimum. However, when the graph starts to do its dance around the x-intercepts, so here were the x-intercepts, we see that these graphs have these turning points. One where the graph is at a high value, and that is what we refer to as a local max. Another place where the graph is at a lower value, and we refer to that as our local minimum. Now, you could have a graph that does a lot of these undulations around its x-intercepts. The local maximum will be the highest value of those little undulations, those little hills, if you will. And the local minimum would be the lowest value of those valleys, if we want to call them valleys. All right, and those are what we refer to as our turning points. Now, how do we know how many turning points you're going to have? The number of turning points is dependent on your x-intercepts and whether or not those x-intercepts are repeating. So here we have two conditions. The graph of every polynomial function of degree n has at most, n minus 1. So, for example, if I had a 4th degree polynomial, it will have at most 4 minus 1 or 3 turning points. Condition number 2, if a polynomial function has n distinct real zeros. So here we're talking about if it was a 4th degree polynomial, and each of those zeros were real and they were different. So for example, if I had a 0 of -1, 0, minus 1 turning points. So the difference is, condition 1, maybe you have a repeating 0. Condition 2, I have no repeating zeros. So condition 1 could be a 4th degree function that only has 1 turning point. And that's a graph that kind of looks parabola-ish. It would kind of look like this and flatten out and go up. That could be a 4th degree function, but only has 1 turning point. So that's how we can tell what the graphs are kind of look like by looking at the function's 0 values. And then n minus 1 is the good indicator here for the either maximum number of turning points or the exact number of turning points. So let's turn those scenarios here into looking equations. For example 2, looking at the equations for example 2, graph the function and identify the x-intercepts and the points where the local max and minimum occur. Okay, so again, we're going to look at where the max and mins are occurring. We're not going to necessarily find the exact value of where that happens. So the difference here between example 2's problems and example 1 was in our factored form, which we love because it makes it very quick for me to graph by finding my zeros. Now we have some work to do. I have this 4th degree polynomial. I can't group it, can't factor GCFs out of this thing, so this is where now I go back and pull out of my tool belt the things we've been working on so far. I have the rational 0 theorem. And this is where I'm going to take a look at my p's and q's. So the p's, again, are the factors of the constant term, so plus or minus 1, 2, and 4. The q's are the factors of the lead coefficient, plus or minus 1. And whenever your q is just 1, that means your p and q's will just simply become your p values. And the p over q's, that ratio again, these are what we test in our synthetic division problem. All right, so we go ahead and we make sure our polynomial is in descending degree order. If there's any missing powers, I'm going to put a 0 in here. That's not the case for this one. So coefficient of 1, and then 4, and then 3, and then a negative 4, and then a negative 4. And we're going to go ahead and test. P's and P over Q's, 1, 2, and 4, and all these are plus minus, by the way. So let's just test the 1, see what happens. 1 and 1 is 1, 1 plus 4 is 5, 5 and 3 is 8, 8 minus 4 is 4, 4 minus 4 is a 0. All right, found a 0 right off the bat, and not always going to be the case. And then I, again, am talking to you guys about continuing the synthetic division process in the shortcut method. What I would do right here, if I know that 1584 is my new cubic, because I found a 0. Well, now I'm going to consider using 1584 as a new polynomial with new p's and q's. Now, it just so happens that the p's and the q's come off of the same numbers, 4 and 1. That's not always going to be the case, but in this problem it is. So I am able to use the same p over q ratios and try now synthetic division on this group of numbers. This group of numbers right here. So like I'm ignoring right now the original set of numbers that I had done because I had already now found a 0. We're going to reset this thing. All right, so we go and let's say I'm going to test a 1 again. So here's the advantage of doing it this way, and I would encourage the synthetic division process to be done like this. If you were to just simply go with 1, 4, 3, negative 4, negative 4, the original polynomial, and test all of the p over q ratios and find your zeros, you might get lucky and find all of them. There is a chance, though, that you have a repeated 0, a multiplicity issue. And you won't catch that if you just run through all of the p over q ratios with one polynomial. So I am always the advocate of, you do the polynomial until you find a 0. Once you find a 0, you reset. So we're resetting here, and now we're doing 1, 5, 8, and 4. So 1 and 1, 1 and 5 is 6, 6 and 8 is 14, and 14 and 4 is 18. So guess what? No, we didn't find 1 there. All right, let's try a negative 1. Negative 1 and 5 is 4. Negative 4 and 8 is 4. Negative 4 and 4 is 0. So we found another 0. Okay, now at this point, we have gone from a quartic down to a quadratic, where this is x squared plus 4x plus 4. Now we can set this quadratic equal to 0. If it factors, great. If it doesn't, we can just use quadratic formula. This one does factor, and it factors into an x plus 2 quantity squared equals 0. And so I know 0-wise that x would equal negative 2 for this one. And I will, again, be paying attention to the fact that I saw the same factor twice. So that's what's giving us this power of 2. And I'll remember power of 2's on factors is an even power. That means I'm going to have a tangent situation or a bouncing situation that occurs at x equal negative 2. So all of my zeros so far, my zeros are x equals, that's a sloppy x is equal to a negative 1, a positive 1, and a negative 2. If I wanted to, I could write this thing into factored form. It's not asking me to do that, but I could. F of x is equal to an x plus a 1 times a quantity x minus a 1 times an x plus a 2 quantity squared. There's my fourth degree. So that's the factored form of this original f of x function in expanded form. But let's use all of our factors here and see if we can draw our sketch. So, negative 1, and 1, and negative 2. Okay, if I do this right, I'm going to bounce off of that 2. Looking at the degree of the function, can't forget to do this, our degree is even, fourth degree, and our lead coefficient is positive. So I know a fourth degree function, even, it's going to start up on the left, it's going to end up on the right. It's going to, because it's positive lead coefficient, and it would look something like this. All right, so it asks us to graph it, identify the x-intercepts, we've done that, and the points where the local max and min are going to occur. All right, so we've identified our x-intercepts. Where will the local max and mins occur? Well, this has a very small local max. We see this part of the graph right here, where the bounce occurs, and then I have to make a quick change between my two x-intercepts. So there is a local maximum in that area, and it's right there. And in terms of the value, it looks like it's somewhere around 0.3 or something. We don't know exactly what it is, but I do know that it is occurring between negative 2 and negative 1. Again, if I wanted to find the exact value, what we could do right now for what we know is we can just start plugging in decimal values of negative 1.9, negative 1.8, negative 1.7, negative 1.6 for our x values, and see which one gives me the largest y values. That's an approximation process. The best way to do it is through the use of a graphing calculator. We can use the calculate maximum function on the calculator to do that. And we're going to have a problem here at the end where we actually get to visit that. So there's my local max, somewhere in between negative 2 and negative 1. And then I have this valley part of my curve, and there's my local min. And it appears that that one is occurring somewhere between 0 and 1. Again, in terms of what the value is, it looks like it's about negative 4.9 or 4.8, something like that. And there we go, fourth degree function. Let's try this next one. Okay, we're back to factor form, which is nice. Degree, let's see, we have a power of 2, power of 1, so we're back to an odd function. This is a third degree. Lead coefficient, got that 2 out there, and that's positive. So I know I'm going to start in quadrant 3 and end in quadrant 1. And then we can go find our zeros. So we have x equal 1 and x equal special case because we're going to bounce off of it. Let's see what we get. X equal 1, x equal 4. And there it is. Really kind of hugs the negative y-axis there that goes into quadrant 3, so it's kind of hard to see it. We have ourselves a local minimum. No local maximum here, but we do have a local min. Looks to be -8, and it looks to be at about 3. So one way I could check that is I could put a 3 in for x and see what I get for y. So 3 minus 1 squared, 2 squared is 4, 4 times 2 is 8, and 8 times -1 is -8. So yeah, it looks like it's 3, -8 is where that local maximum or local minimum would be occurring there, just simply by testing the point. All right, so there we are with our graphing components. Now let's actually do some application to this. One of those applications commonly is found in materials, building containers and maximizing your volume while minimizing your surface area or the amount of material that you can use. So here we have a case where we're going to take a cardboard box, a rectangular cardboard piece, and we're going to cut and shape it into a cardboard box. So this is what happens in industry. They just have the raw materials, and then they take that and they build from that their containers. So we have a little visual here on the left-hand side. Now these hidden lines right here, these guys, those indicate the fold lines of this box. You can imagine we started out with a box that was a full piece of cardboard. So it would have been looking something like this, a rectangular piece of cardboard to begin with. And then what we did to make it become a box is we had to cut out those corners. We had to remove these corners on the side so that I can create these little wings, if you want to call them, that fold up and become the height of the box. So you can imagine, for example, this piece right here folding along this line and becoming the height portion of our box. So this area here is like the bottom of the box. This is the left side. This is the right side. This would be called front and back. This is the back of the box. This is the front of the box. So it's kind of hard to maybe visualize what's going on, but if you actually were to take a piece of paper and do this, take a piece of paper, cut out the 4 corners, and then where those corners meet here, take those as fold lines, you would physically see a box that would result if you were to fold it along those corner lines. So that's what's happening. We want to have the maximum possible volume. So that's an important piece right there. Greatest possible volume. How long should we make the cuts? So the cuts are these values of x. Now notice you're making the same cuts. So you're cutting out squares from the corners here. And then what is the maximum volume going to be? So we got to make sure we understand the problem before we jump right into it. One of the things you're going to need to know here in working with a volume of a rectangular prism, which is what a box is what the equation for the volume of a box is. And hopefully you know that, but if not, we'll help you here. Volume is a width times a length times a height. That's what a volume of a box would be. All right. So where do we go from here? And this would be a great place, if you're trying to work on this on your own, I'd love to give you some think time about this. So this would be a great place for you to pause and pause the video and start trying to work this out as best you can. And then after you've given it a shot, come back and check in with the video and see how you did. One of the first things we need to do is determine these lengths here. What is it from here to here? turn, what is it going this way? Because those define the dimensions of what we will call the width and the length of my box. Remember, the h is going to be the x value. That's the height of my box. All right, let's work with the 30 dimension. So the overall, from the edge of the original piece of cardboard to the edge was 30 inches. But we're not going to end up with that for our box. We're just going to end up with just this piece in here. That size. Well, how we got that size was we took out these corners, and those corners each had a length of x. So that means that question mark would have a length of 30, the original, and minus the 2x corners. And this length over here same concept, started with 22 inches, and we removed the 2 corners. And now we have the dimensions of the width and the length of our box. And again, height is going to be that x component. So we can write our volume as a function of this length x is equal to the length, 30 minus 2x, the width, 22 minus 2x, the height, x. Everything is in terms of x. That's good. And then now we're going to go ahead and expand this. I could expand it, come up with my equation. Let's see if we were actually supposed to. We're not. We're looking for how long should the cuts be and what is the maximum volume. Okay. So I could expand this right now and come up with an equation for our volume as a function of x. But I could actually, at this point, go ahead and find my x-intercepts. These x-intercepts, again, help me to draw this graph. And the reason I'm able to find the x-intercept is I'm at a point where I have factored form. And if I just made volume equal to 0, then I am able to come up with my equation, or my x-intercepts. So we have our zero product property for each of these parts. And we discover that x is equal to 15 here, and x is equal to 11. And since we're talking in units, we're going to talk about them being in inches. All right. So there's what we have, our 3 x-intercepts. We can put those x-intercepts on my graph. So if I were to do that, I'd have an x-intercept down here at 0, and then I'd have one at 11, and then I'd have one at 15. There's my x-intercepts. And then from here, we can go ahead and graph. Now again, we kind of need to know what the degree of the function is. Power-wise, I got an x to the first, an x to the first, an x to the first. It's got an x to the third as the degree of my function. So here's where, again, maybe it would be helpful to go ahead and expand this. Let's go ahead and do that. I'm going to do the 30 minus 2x, 22 minus 2x part. Foiling that out, we get 30 times 22 is 660. And then minus 60x minus 44x is minus 104x. And then negative 2 and negative 2 is 4x squared. And then this would then get multiplied by x. And then we have our volume in expanded form. Putting it in degree order, 4x cubed minus 104x plus 660x. So we can see lead coefficient positive. There's our odd degree. I know this thing's going to start low and high. Okay, so we graph it. And I already have it here. So there's what it looked like. Yeah, we had to make our y scale very large here to account for the volume. So let's talk about our axes for a second. So the y-axis is the same as our volume as a function of x. And our x-axis, again, is this length that we're cutting away. So we can see that the maximum volume is going to be somewhere around 1240-ish. It's occurring right here. There's where the max occurs. That's our local maximum. This graph does have a local minimum, but I'm really not interested in that because that would be negative volume, and that's not useful for us in a box. So now if we actually wanted to go find the value of that maximum, and determine what value of x is going to make this the biggest box possible, here's where the graphing calculator can come in. Now, graphically, we can kind of interpret, it looks as though, let's see if I were to come off of that point, come straight down, and it looks like we're somewhere just a little after 4 would be the value of x that maximizes this, but we don't want to guess. We're going to actually come up with the real value through the use of the graphing calculator. So here we go. Let's minimize this for a second. Let's get a graphing calculator up here. And we're going to put this equation in, and we're going to use the graphing calculator feature that allows me to find our maximums. And that will then tell us what our value is going to be. All right, so here's our graphing calculator. We're going to put in our equation, and I'm going to put it in with our expanded form. We had 4x cubed, 4x cubed. Oops. There we go. Doing our graph. So 4, whoops, back up. 4x cubed and negative minus 104x squared oh, that's not what we want. Sorry about that. Let's try it again. 4x cubed minus 104x squared plus 660x. All right. Where did it go? Minus 104x squared plus 660x. There we are. Kind of hard to see. Oh, where did it go? There it is. So my axes are really tight here. It's not allowing me to adjust my window properly if I wanted to see my entire graph. So let's just go with the fact that it does work. I can actually put it in here and adjust my window and see my my graph to its fullest. But what you could do now is use the menu option and then analyze my graph. And we would go find our maximum. Now, I'm not physically going to be able to see the part of the graph right now that shows me where that maximum occurs, probably because I'm just a rookie with the calculator here on this stuff. But I would actually put that in, and it would calculate my value for me. And it just so happens that it would be 4.18 is the maximum length that gives me a volume of 1233.81. My lower bound is somewhere over here. My upper bound is somewhere over here. And there it is right there. 4.18, 1.23 times 10 to the third is what that means. So 1233. There's your maximum. So there's the use of the graphic calculator. And that's what we would have for our value here. 4.18, 1233.81 cubic inches. And this would be inches. So these would be my units that would determine my maximum volume. Sorry about the window issue on the calculator. There we go. I hope that was helpful.